Hello.
Hi, good morning. How are you all?
Morning.
Hi. Morning.
Good morning.
I
Right.
don't know if I hear you, Professor Bowen.
Oh, can you hear me now? I haven't really been saying anything. Yeah, can you hear me?
Oh,
Yeah, here. I need to go get the power strip. I'm actually running late, so I'm actually here at home. So give me just 1 second so I can get my power strip. It's not recording. Okay, now we're good to go. All right. So let me just start with just a few quick announcements. Wednesday's lecture is up on YouTube, so hopefully you'll be able to see everything right there. I'll have office hours, usual time, usual place, so 11 to 12, just after class, and then 4 to 5 in the afternoon today. And of course, the next homework assignment is due today, so please try to upload that to Sakai. If you have any issues, just let me know. You can also just send me things by email. I'll try to have the next homework assignment posted some point, if not today, then tomorrow. So that'll be homework assignment number 7 that'll be due by next week. So any questions about anything before we do get started on our recap? All right. So remember that on Wednesday, we quickly went over the 4 isomorphism theorems, and then we talked about a couple of applications of these. So by a ring homomorphism, remember that we mean a mapping between 2 rings with identity, where we have to keep track of elements going to elements, addition kind of being preserved, and then multiplication being preserved. We had the idea of the kernel and the image. The kernel is a subring of R, which is the set of elements that map to 0. And the image is a subring of S, which is just the set of elements that look like they come from some element in R. So the first of our 4 isomorphism theorems says that the quotient here, R mod I, where I is the kernel, is a subring of the image. So again, the image itself is a subring of S. So now this says that the quotient ring R mod I is a subring itself of the image. The diamond isomorphism theorem kind of gives us a way to get a little bit more information about other subrings and other quotients. So this is that, let's say that we're dealing with the ring R, we have 2 things. So A, let's say perhaps is a subring of R, and B is an ideal of R. Then it says that we have the following quotient, right? So A plus B mod B is isomorphic to A mod A intersect B. The way that you can read this is B itself is an ideal of this ring A plus B, the subring A plus B. And that's the same thing as A mod this, where A intersect B is an ideal. And so then A mod A intersect B, of course, is also going to be some subring. So this says that there should be some relationship between all of these. The third isomorphism theorem now tells us this idea of invert and multiply. So here, if you have, let's say, 2 ideals, I and J, where J is the larger of the 2, then the quotient, J mod I, is also an ideal of this quotient, R mod I. And the second part, this is the invert and multiply part. If I wanted to look at R mod I quotient J mod I, in some sense, I just get rid of the i's, and now that's just the same thing as R mod J. So I'm going to use this third isomorphism theorem a little bit today. We'll then have the fourth isomorphism theorem, also known as the lattice isomorphism theorem, and this gives us a one-to-one correspondence between ideals of the ring R and ideals of the quotient ring R bar. So I'll write it this way here. A is an ideal of R containing I if and only if A mod I is an ideal of R mod I. So again, we're going to come back and talk about this here today, but this kind of gives us this nice correspondence of saying, if I look at R bar as itself a ring, then I know exactly what all of the ideals of R bar look like. They're all in the form A mod I, where A is an ideal containing I. So here's one direct application of the lattice isomorphism theorem. This says, let's pick a commutative ring and let's let I be an ideal of this commutative ring. So then, of course, we can talk about this new ring that we can call here R bar. And this says that if I look now at the prime ideals of R bar, those correspond exactly to the prime ideals. They're wedged between I and R. And similarly, the maximal ideals of R bar are those maximal ideals of R wedged between I and R. So if I want to know something about the spec of R bar, I just need to know something about the spec of R. And if I want to know something about the M spec of R bar, I need to know something about M spec of R. So we're going to use these two concepts here later on today as well. From here, we then moved into polynomial rings. So now let's say that we have a field, and let's let R be the polynomial ring over n variables. And you can define this in an inductive way if you want. So the statement is, if F, our field, is an integral domain, and every field is an integral domain, then R itself, the polynomial ring, is an integral domain. So there are really nice ways in which we can generate more and more and more integral domains. So we're going to use this today as well. Now there's a way, once we have our integral domain, to generate ideals. So say that we have a collection of polynomials. Right? So this set S is just some collection of polynomials. And now what I want to do is consider the ideal generated by those. What I mean is, I want to consider linear combinations of this collection of polynomials. Right? By linear combinations, what I simply mean is that I have these here where, if you will, the coefficients that I'm allowing to use, right, the g's here, those all have to come from the polynomial ring R. Right? So just kind of take these linear combinations where I'm allowing myself to multiply by other polynomials. So again, this here is an ideal. So this tells me inside of my integral domain R, I can generate lots and lots and lots of ideals. So one question you can ask is, what are the maximal ideals of this polynomial ring? So let's focus on the special case where the field F is algebraically closed. And if you're not really comfortable with that, you can just say let F be the complex numbers. Right, so let's let F be an algebraically closed field. So then, as I just mentioned, the polynomial ring is an integral domain. And so if it's an integral domain, we can then ask something about the maximal ideals. So this says that the maximal ideals are actually generated by polynomials in a very specific form. So every maximal ideal is generated by these polynomials x1 minus a1, x2 minus a2, so on and so forth. Where, of course, by generated, I mean exactly the statement that's here. Right, so this is what I mean by saying generated by these polynomials. Okay, so again, if we're working over an algebraically closed field, so think of F as like the complex numbers, then the polynomial ring is an integral domain, and I know a lot about the maximal ideals in such a ring. So this is another concept that we're going to use quite a bit today. Right, so any questions up to this point? Okay, great. So can everybody hear me okay? Is the lecture going okay so far?
Yeah, it's okay.
Okay.
Yeah, it's good, thanks.
Okay, all right, thanks for that. Okay. Now quickly, I just want to remind you what we then said at the end of the last lesson. So remember, we can define affine n space as just the set of these tuples. And so if we have our polynomial ring in n variables, then our ideal is prime if and only if the quotient here is an integral domain. So again, we look at our ideal I generated by these polynomials. It'll be a prime ideal if and only if the quotient ring is an integral domain. This again goes back to how we're going to kind of focus on integral domains. So we ended the lesson by discussing this very general idea of an affine variety. So what we can do now is, given an ideal, let me denote this VI of F as the set of points that vanish at all polynomials in our ideal. If you're not comfortable with that, you can simply say it's the set of points that vanish for all of the generators of the ideal. So here if I have M generators, so F1 through Fm, remember that they're just polynomials that somebody gives to us. Let me find out the set of all points where they are simultaneously equal to 0. Well then, of course, if these are all equal to 0, then I can take any linear combination of the polynomials, and then that's what I mean by this set here. Right? I can take any linear combination, and then these will also be equal to 0 for all polynomials in the ring. So when I write x here, I really mean x as a polynomial, not just x as a variable. So this is what I mean now by an affine variety. So I can define a variety based on an ideal. So we end it by saying, once we have this, then we can view any element of this quotient ring as a function. Right, so again, any element here of this quotient ring is now just a function where if I take a point P on the variety, I can evaluate f at P. Part of the reason this looks a little bit weird is that remember that we're dealing here with a quotient ring. So it's not just like we just have a polynomial and we're evaluating for a polynomial. What's a little bit bizarre here is that it really is a quotient ring, so you have to be a little bit careful as to the definitions. But still we have our variety. We still know what an affine variety means. It's a set of points. And so I can just evaluate now at these points. Okay. So to kind of step back a little bit, we know that we can identify elements in this quotient ring. All right, so here we have the polynomial ring, modulo our ideal, with functions. Where now let's focus on this affine variety. All right, so again, this is what we just said, that we can identify elements in the quotient ring here with functions in this variety. Okay. But what do we mean by functions? So for example, what can we really say about these? Can we say anything about that these functions are continuous, that they're smooth, so that is that they're differentiable? So what do we really know about these functions here, other than that they're just functions that we can write down? Well, in order to make sense of what do we mean by properties of these functions, we actually need to introduce a topology. And those of you who've taken analysis, you probably remember that we say these fancy words like a function is continuous if and only if the inverse image of an open set is an open set. So in some sense, if you wanted to try to say something fancy about functions are continuous in the sense here, we have to make sense of what an open set is. So this is going to be one of our two goals for today, is to try to make sense of what an open set is, so then we can start to place some of these fancy adjectives on our functions, things like they're smooth or continuous or what have you. So here are two definitions that we're going to use today. Fix an affine variety, call it X. And again, by an affine variety, I mean exactly this definition that's sitting up here. So I have just some collection of polynomials, F1 through Fm, and I just want to know the zero set for this collection of polynomials. I'll say that a subset of X, let's call it V, is closed if I can find a collection of polynomials, which I'll call T, such that V is the zero set for that collection of polynomials. So here T could be a finite set, it could be the empty set, T could be everything. It could be every polynomial and n variables. So T here is just any subset that you want. Again, T could even be the empty set. So all that I'm asking here is whether V is the zero set for this collection of polynomials. Even if this is an infinite collection of polynomials, is it still a zero set? This is what I mean when I say that a subset is closed, that it's in this form here. So Z here, you can think of this as Z stands for zeros. So the zero locus for this collection of polynomials. On the other hand, I will say that a subset is open if it's the complement of a closed set. Right, so I have the idea of a closed set. Now I take a look at the complement of that. Right, so I'll try to give some examples of this a little bit later. But again, this is the concept of a closed set. So it just means zero locus of a collection of things, and the concept of an open set. So it's the complement of a closed set. All right. So now I want to introduce a big theorem, which is perhaps the biggest theorem here with these definitions. Again, say that X is an affine variety, so zero locus of some collection of polynomials. I claim that both the empty set and the whole set are open. Right, so I claim that both the empty set and the whole set are two examples of open sets. Number two, say that I have an arbitrary collection of open sets. So here this is supposed to be read, the collection of U sub alpha such that alpha runs over some indexing set I. So I might have here like infinitely many open sets. I might only have finitely many open sets. But the point is, let's just say that I have some collection of open sets. Then the statement is that the union of open sets is an open set. Right, so again, if I have a collection of open sets, then its union is also open. And finally, if I have a collection of open sets, but now I only want finitely many, right? So here I have an indexing set I, so I could be the numbers 1, 2, 3, 4, 5. I is just some indexing set. And here I'm assuming that there are only finitely many elements in this indexing set. It's only finitely many numbers. Then I claim that the intersection of a finite number of open sets is an open set. So again, we have three properties. Number one, both the empty set and the whole variety are open. Number two, the union of a collection of open sets is open. And number three, a finite intersection of open sets is open. So if I put all of this together, then let me let U alpha here denote the collection of all open sets in X. Right, so again, the collection of all open sets. Then I'll say that this pair, my whole space with the union with the open sets, is called a topological space. And the collection of open sets is what I'm going to call a topology. So these are just some fancy terms here. So again, if I take just a collection of open sets, so you'll notice that this is a little bit weird because I can start with two open sets. I can start with the empty set and the whole space. I can union open sets to find more open sets, or I can intersect open sets and find more open sets. So the point is that there are lots and lots and lots and lots of open sets. There are lots of ways I can write down open sets. So if I put them all together, there probably are infinitely many of them, but if I put them all together, that's what I call a topology. And this pair where I have my space along with the topology, those two are what I'm calling a topological space. So before we go over some examples, I just want to remind you that for the moment, this is just like an abstract definition. So there really aren't any pictures that I can draw here. Right now, I'm just kind of doing everything in an axiomatic way. So the idea of an open set is in terms of these things called closed sets. So I have now here things like unions and intersections, but it's very difficult to kind of wrap your head around what does this look like. And this is one of the unfortunate things in algebraic geometry. It's really impossible to draw pictures to kind of understand what all of this means. So for the moment, we're just going to think of this as like a black box. So we're just going to write things down without really trying our best to understand what's going on here. So this specific topology, where remember we're defining open sets to be in this form, is what we call the Zariski topology. So this is named after a professor who was at Harvard University for a long, long time named Oscar Zariski. In fact, there's actually a bust of Zariski that's in the common room there at Harvard. So the Zariski topology is kind of the natural way in which all of us in algebraic geometry do topology. Whenever you see any topology at all in algebraic geometry, it's probably going to be this weird kind of Zariski topology. So I want to try to go over some proofs of these statements to hopefully explain what's going on, and then I'll try to go over some examples of these here. So any questions for the moment just on the definitions here of open and closed and what the Zariski topology is?
Could you like show me the definition of open sets again?
Yeah, it's right here. So an open set means that it's the complement of a closed set, and closed set means I take a collection of polynomials and I just ask, what's the zero set?
Oh, okay.
Yeah, so you really want to think of an open set as somehow related to like a collection of polynomials.
Okay, so it's like given a set, if we can find several polynomials such that the set is the common zero of this polynomial, so the set would be closed.
Right. That's right. You call that Zariski closed, and then the complement of that is Zariski open.
Okay, thank you.
Yeah, you're welcome. And of course, there should be a homework problem coming out next week where you'll actually get to play around with this a little bit and see some more of what's going on. Okay, so let's try to actually do some proofs here. And this is where I want to try to explain what's going on. Let's start with the very first statement that both the empty set and the whole space are open. Now, let's look at the zero polynomial. So the polynomial where it's always equal to zero. For the zero polynomial, then it vanishes everywhere in the space. So that's this first statement here, that the zero set of the zero polynomial is the whole space, right? Because again, if it's the zero polynomial, then it's always zero. So that's what it means to be the whole space. Now let's take a look at the polynomial, the constant polynomial equal to 1. Well, this is the constant polynomial. 1 is never equal to 0. So no matter what you plug in, this constant polynomial is never equal to 0. So that's exactly the statement here, that the zero set of this constant polynomial is the empty set. Because again, there are never any points where this constant polynomial is equal to 0. So the zero set of the zero polynomial is the whole space. The zero set of the polynomial 1 is the empty set. So these are two examples of closed sets. So now I can look at the complements. So the complement for the zero polynomial, of course, is the empty set. And the complement for the constant polynomial 1 is the whole space. So here's a weird concept. Both the empty set and the whole space are both open and closed. So you have to be a little bit careful that it is not true that if something is not closed, then it is open. Because in this case, we have something that is not closed and it's open, and something that is closed, but it's also open. So just because it is not closed doesn't mean that it's open. The concept of not closed is a little bit weird, and it's something we're not going to talk about here in this class. But now we're just simply saying that closed and open, you can have sets that are both closed and both open. Right. Okay, so now let's try to show 2 and 3. So this is the whole thing about looking at unions of open sets and looking at intersections of open sets. So let's say that we have our open sets, U alpha, and we're going to write them as complements of these closed sets. So let's say that each U alpha is associated to some closed set V alpha, which is associated to some collection of polynomials, call it T alpha. Right? Now I'm going to write down some weird identities, and this here is related to what are called De Morgan's laws. And I'll just skim over De Morgan's laws in the following way. The union of open sets really corresponds to the intersection of closed sets. And similarly, the intersection of open sets corresponds to the union of open sets. Sorry, the intersection of open sets corresponds to the union of closed sets. So again, unions correspond to intersections, intersections correspond to unions. That's what De Morgan's laws state. Now, the hard part is to see that if I have the zero locus, then I can kind of use that to talk about the zero locus of the unions. And if I have the zero locus here for the unions, that should correspond to products. So I want to spend some time to talk about these last two here, because these here probably don't make any sense. But at least hopefully it makes sense from De Morgan's laws that if I look at the union, that corresponds to the intersection, and then the intersection will correspond to the union. Okay. All right, so let's try to talk about this in a bit more detail. So let me try to focus on the very first one here. All right, so what does this mean? So first of all, let's take a look at the union here. All right, so here I'm taking a collection of subsets T alpha inside of our polynomial ring. Well, if I have a collection of subsets, the union of those is still a subset. Right? There's nothing fancy there. If I just have subsets, I take the union, I still have subsets. Now I want to ask something about what happens when I try to set things equal to 0. So let me try to say things in the following way. Pick a polynomial from T. Since T is the union, that polynomial appears in T alpha for some alpha. But now if I have the polynomial here, I can look at when that polynomial is equal to 0. But if it's equal to 0, then that means it's sitting here inside of V alpha. So now, if I really take a look at, say, anything coming from T, so now I have a lot of polynomials in T. They have to come from the different alphas here. So if I want those polynomials to all be 0, then that's where the intersection comes in. So again, if I take a lot of polynomials from T, and then if I want them to all be 0, that's what the zero locus of the union means. I want them to all be 0. That's where the intersection comes in, right? Because the word all really means intersection. So that's where the first part here is coming from. Right, so again, if I take something that comes from the union, I want them to all be 0. And so then I want that here to be the intersection. But according to De Morgan's laws, the complement of the intersection is the union. Okay. So any questions here on how we did the first part with the union of open sets? Right. Okay, let's try to move on. What about this weird thing over here with the intersection? Right. Now let's assume that we only have finitely many open sets. And if you will, you can write them as like just this finite set here. Right, so I'm only going to talk about finitely many. Let me make the following definition. I want to consider the product of polynomials where each term here in the product looks like it's coming from one of these alphas. So for example, if I maybe had 2 here, then I'm kind of taking F alpha times maybe F beta, where I take one from the first T alpha and I take the other one from the T beta. So I'm kind of picking 2 at a time. That's what I mean by the product here. I'm just taking products of things where each one comes from one of the T alphas. So like a T alpha 1, a T alpha 2, so on and so forth. I only have R of them, So I only have r of them in the product. Now, part of the reason I'm doing the product is as follows. If the product equals 0, then that means at least one of the factors is 0. They don't all have to be 0, right? If the product of two things is 0, then that means either one is 0 or the other one is 0. It's like if I tell you, take a look at x times y. But now x and y are variables. So what if I solve x times y equals 0? Well, then as variables, either x equals 0 or y equals 0, I don't have to have both of them being 0. So that's what's happening here. It says that if I want to take a look at the 0 locus, then I want either f alpha 1 equals 0, or f alpha 2 equals 0, or f alpha r equals 0. But if I use the word or, that's where the union comes in. Right, so again, the product, setting the product equal to 0, means that one of the terms in the product has to be 0, but that's where the or comes in, and that's exactly where the union comes in. So again, the product should correspond to the or. And again, De Morgan's laws say that the complement of the union should now be the intersection. So that's exactly the statement here. Right? But hopefully I've emphasized that part of the reason why I need to assume finitely many is I have this product here. And I can't make sense of this product if there were infinitely many elements here to choose from, if there were infinitely many elements from the indexing set I. Okay, so does this kind of make sense so far?
Yeah. Yeah, it makes sense. A lot of sense.
Okay, all right, good. Okay, so let's try to work through an example here so we can really hit home what's going on. Right, what I really want to do is kind of use this to motivate maps between varieties. We're going to come back and talk about this later, but some of this is to help motivate what's going to happen. For the moment, let's pick a field, and I'm going to assume that the square root of -1 is not in the field. So you can think of maybe f as like the rational numbers, right? But I don't want to work over the complex numbers, is what I'm saying. I want to consider this polynomial, x squared plus y squared minus 1. And let's focus on this polynomial ring. So just over two variables now. Now I can focus on this variety, which is the 0 set of this polynomial. So of course, this here is just the unit circle, right? It's nothing fancy, it's just gonna be the unit circle. I also wanna write down this projective variety, y, which of course we know is the projective line. So again, I have the unit circle, I have the projective line. So these are two varieties that we've been playing around with. Now there's a map, sorry, it's a typo here, that takes us from projective space to the variety, which we've been playing around with over and over again here in this class. Okay, so again, we just have this map here, which plays around with this projective variety. So it says, given a projective point, I can write down this affine point. So here's a map, call it psi. What I'm going to do is prove that this map is birational. And again, we're going to kind of focus on these definitions more later, but I'm trying to use a lot of this to kind of motivate some things that we're going to see later. So with this map, I want to prove that there is another map, let's call it phi, where if I look at these two compositions, so psi composed phi should be the identity on x, and phi composed psi should be the identity on y. So again, I want to try to find another map where kind of the rough idea is that the composition here should look like the identity map. And so we're going to play around with open sets here to kind of get an idea of what's happening. So let's consider these two open sets. So here now, remember, we're just dealing with the circle. So what if I take away the south pole of the circle? Right, so I'm going to delete -1, 0. Right, so delete the point that's way on the very left of this circle. So if you really think about it, if I have a circle If I take away 1 point, that should look like an open set. Right? That's kind of the idea. So I have like this circle, kind of cross out 1 point, that should be an open set. Well, in our rigorous definition of Zariski open, yes, it is open, because if I set x1 equal to -1, that's exactly this point here. So the zero locus of this polynomial is 1 point. Right? Again, the zero locus of this polynomial is just 1 point. So the complement of that zero locus is this open set. Okay. Similarly, let's take a look at this here. This polynomial, x1 minus 1, I can look at the zero locus of that. That is 1 point, namely the point 1, 0. That's the zero locus. So this set here consists of just 1 point. If I look at the complement of that, that here will be the set of points on the unit circle where I stay away from the right-hand side, so I stay away from 1, 0. Right? So if I stay away from 1, 0, then this here should be open. So again, U1 and U2 now should be open sets. And hopefully you can kind of see with the picture why they have to be open sets. Now, I also notice that I can think of X here as the union of these two. Now, of course, there's a lot of overlap here, but the point is that if I kind of take the whole circle minus the left-hand side, or if I take the whole circle minus the right-hand side, then I just get the whole thing. So the whole point here is that the union of those two, right, again, there's a lot of overlap, but I get back everything on the unit circle. So for the moment, I'm going to call this an open cover, right? Because it just says that it's just everything all together, but I'm doing it because I have now two open sets. Now, let me define two maps. So first, let me define a map, phi1, in this way, that will take a point, x1, x2, and let's consider this here. Right, 1 plus x1 divided by x2. Of course, this here is well defined because I'm staying away from -1, 0. So I can't have simultaneously 1 plus x1 equal to 0 and x2 equal to 0. The reason being this here. Right, so this here is a well-defined map. Similarly, if I go here to phi2, this is also a well-defined map because I cannot simultaneously have x2 and 1 plus x1 equal to 0. The reason being exactly this here. Right, I'm staying away from that point, so I can't have both x2 equal to 0 and x1 equal to 1. Right? So any questions here on how we define these two maps? Okay. All right. So now what do we know about these? Well, we're working with the unit circle. So I realize that here we have this equality. Right, so 1 plus x1 over x2 has to be t1 over t0, but that's also equal to x2 over 1 plus x1. The reason I know that that's true is, well, you can just kind of stare at these formulas. Right, if you just kind of use this for x1 and x2, you plug everything back in, then you get this here. But now, here's what this means. These two functions are actually equal. Right, that's exactly what this means here. So 1 plus x1 over x2 equals x2 over 1 plus x1. Right, that's exactly what it means to say that these two here are equal. Of course, they aren't equal everywhere. They have to be equal here on this intersection because I have to stay away from these 2 points. Right, if I stay away from those two, then both sides are equal and everything's okay. Right, so now you'll notice this kind of weird thing. I'm going to say that here I have two functions that are equal because they are equal on a Zariski open set. All right, so again, I'm going to say the two functions are equal if they are equal on a Zariski open set. All right, so we're going to come back and play around with this in more detail, but just for today, this is supposed to kind of give you an idea of how this stuff is going to work more generally. So now we have the following. definition. We'll say that our morphism, phi, right? Remember, this is the one that we wanted to talk about originally. I'm going to define in the following way. Remember how X was the union of U1 and U2. Right? Remember, X was the union of those two. So I can talk about points in the first set U1. And if they're in U1, I know how to make this definition. This is what I was calling phi1. On the other hand, I can pick an element from U2. And I can say, okay, fine, here's the definition if I'm on U2. Now you might ask, well, how do I know that everything is well defined? Because I've defined it on one set, I define it on another set. Here's why everything is well defined. It's because on the intersection, these two definitions are equal. So it doesn't matter if I pick an element from U1 or if I pick an element from U2, or if they're even from both, because the functions here are equal. And so now it's just a matter of checking that the compositions here really are the identities, like what I've said. So here's kind of the weird thing in algebraic geometry. You sometimes want to write down a function, but you have to be careful as to how it's defined. Like in this case, we've defined part of it on one open set, I've defined part of it on another open set, and then I have to make sure that these two definitions are compatible if I look at what's happening on the intersection. But still, this is the philosophy in general. So later on, we're going to talk about this idea of gluing, which says that you can kind of talk about one thing, you can talk about another thing, and somehow you want to glue the two of them together. Gluing just simply means that they better match on the intersection, that everything here better be consistent. Okay, any questions on how we've done this here? Okay, I think what I want to do is I want to call it a day. There's some other things that I did want to say about abstract varieties, but I think for the sake of time, what I'll do then is I'll wait until Monday. So I'll go ahead and I'll post, excuse me, the next homework assignment, if not today, then it'll be up by tomorrow morning, but that assignment will be due next Friday. So just remember that today, this assignment will be due by 5 p.m. If you need more time to get it done, don't stress, that's perfectly fine. I know everybody is kind of going through crazy times these days. So just do the best that you can at this point. So you have any questions for me before we call it a day?
Professor,
Yeah, sure, go ahead.
go to your office hour this afternoon at 4.
Okay, I will be there. Yeah, I'll be there. There's a faculty meeting, but I'll try to be there for office hours and I'll take your questions instead.
Thank you.
Okay. All right, well, you all have a good weekend then, and hopefully I'll see you on Monday.
You too.
Thanks, Professor. You too.
Thanks.
Take care.
Professor.
Yep, sure.
I just have a small question about like next class.
Yeah.
But should I still attend it, or like are you guys going to be like busy with like the presentations or whatever? Like I don't know what's your call.
I would say go ahead and attend. I think what's going to happen is everyone's just going to present their solutions. So it might be good just to see solutions to some of the problems. You know, that way we'll just kind of cover more material.
Gotcha. Okay.
Okay.
So this is next week?
No, this is for the next class for Math 101. Yeah, totally different.
Oh. All right.
Okay.
Thanks, Professor.
All right, you're welcome.
Nice day.